Hello, everyone. Thank you for being here to our latest webinar dedicated to how to properly use wind data and wind comfort analysis. And today, for this webinar, I will be joined with Guillaume Cagnon,
Hi, everyone.
who is our urban climatology expert since 2010 at Metodyne. And he is the product leader for UrbaWind, and myself, Guillaume Vervou, and I'm the business manager of the urban product line. And we are working together to develop and to propose a new product and new services around the urban world. Just before going into details of this webinar, just to have the summarizing contents of today. So we will come through different points, and the first one will be the presentation of the methodology to assess the wind comfort, following by the brief review of anemometer technology, especially at the weather station. Also, we will have a quick overview on the topographic effect, especially the orography and roughness effect. Guillaume, after this, will present you the first aid kit, and it will be followed by some examples of differences between the weather data and between the mast and the project. Before going for a Q&A session, we will also present you where to collect some data for your first implementation into your simulation. Just also before the first point, a quick overview on Metodyne. So Metodyne, we are existing now since more 22 years, and we are based in Nantes, in France. And we are software developers and experts around the wind energy and wind engineering. And we developed computational fluid dynamics softwares, so CFD softwares, around different expertise, going from the wind energy field up to the urban world and the safety matters. And we also propose services consulting like tailor-made weather and climate services for different type of projects. And on the next slide, I will let the mic to Guillaume.
Hi, everyone. I hope you're fine. So this webinar will be dedicated to know how to conduct a wind comfort study in a good way. I know this is a request by many of you. You are probably familiar with the wind comfort analysis. If you are not, I will encourage you to watch our previous webinar. Do not hesitate to ask us questions in the chat panel or question panel. We will answer you at the end of the webinar. Of course, we will have access to the replay. We will have access to all the questions answered at the end. So very happy to be here today. So let's start. Let's start by some recap of how to assess the process. So you will need the climatology data. It can be frequency table. It can be wind time series. You have some example on the left part. You will need to run several wind direction. So minimum, I would recommend to go a minimum with a 30 degrees step. And then you will post-process those CFD results using your pedestrian comfort rules to compute wind comfort map. So now the question is, how can I be sure that I'm relevant? I can see three bias here that I can explain difference on the final results. The two first are coming from input data. First one is obstacle. So how good is your building definition, your topography, your vegetation, if they are well designed. because they will affect, of course, the wind pattern. Second I see is wind data input, so we'll talk about that. And the third one is the CFD accuracy. For that, I have wrote many papers about accuracy. You can have a look on our webpage. Let's say you can expect 5% error with respect to wind tunnel. So this is quite good results. So let's talk about what is the topic of today is wind data input. And let's talk about the source of wind data, the anemometers. And I will go through, let's say, 4 technology from the primitive technology to more sophisticated. You probably recognize some of them. The first one is a windsock. That's the most famous and most spread around the world. It's mainly set up in small airport or aerodrome. It's not only a weather vane, but it can estimate wind speed. You can see there are red and white stripes, and each stripe that is going to inflate, that's an increase of wind speed, and it can range from 3 to 5 knots depending on the country. For US is 3 knots, that's about 5 km per hour for each stripes, and France it's about 9 knots or 9 km per hour. So multiplied by 5 straps in France, that can be ranged up to 45 km per hour. But it is very basic. It's only visual data, not accurate for our need. The next one is the cup anemometers. This is the most spread around the world. It's quite it's old. It's from the 19th century, from the Robinson inventor. It can measure the wind and the wind speed and the wind direction. So it's made of 3 or 4 cup, or let's say half cup, about the size of the tennis ball. And when the air flow around the cup, the anemometer will rotate. This turns the shaft proportionally to the wind speed. To give you an idea, 1 revolution per second of this anemometer is equivalent to 1 meter per second. It's going to rotate quite fast. It's very easy to set up, and it can range up to 200 kilometers per hour. So it is sufficient for all events, even the extreme events like a storm. Drawback, it cannot catch fast events like gust speed smaller than few seconds. But for our purpose, for comfort, it is sufficient. It also comes with a weather vane to get the wind direction. And it is quite mature, I would say, technology. It's the standard for wind assessment for wind energy. Here in Methodin, when we conduct wind resource assessment, we use this technology. The other one is more anecdotic. It's called a vane anemometer. You see, it looks like a small airplane. The axis of rotation is vertical. And the last one was developed in the 70s. It's called ultrasonic anemometers. And as its claim, it's used ultrasonic wave to measure wind speed. Advantage, it can be set up in a remote location, such as island or platform on the sea. There is no mechanical maintenance, contrary to the cup anemometer, and it can it can catch turbulence very accurately. So it's very nice for, let's say, a safety issue. But globally, what you will find in most of the world is the second one is cup anemometers. Now let's move to the next subject. What is topographic effects? So topographic effects. Well, there is some kind of confusion in the sense that, in a common sense, we talk topography by the effect of the hill, of the mountains, but it's actually more wide than that. In the meteorological sense, topography is a combination of orography and land occupation effects. What is land occupation? Is well, when you have open country, when you have a city, when you have forest, this land occupation. It is also called the roughness effect, and both will affect the wind. So actually, the mean velocity is function of so topography, orography of the site, and roughness effect. It depends also of the height above the ground and obstacle nearby, building, trees. I would like to give you some order of magnitude of topographic effects. So let's start by orography. If the reference is flat ground, and the same land occupation, at the bottom of the hill, it's minus 50%, so less with compared to flat ground, and hill, it's the opposite, plus 50%. If we compare roughness effects, compare if the reference is open country and we are on the flat ground, if you are nearby the sea on the coast, you will feel more wind, and this is about 40% more. Where in downtown, you will feel less wind, up to 50% less. Here we are talking about at 10-meter high above the ground. So I would like to talk about how can we, let's say, estimate topographic effects. So let's start with orography. And there is a good thing is, let's have a look on the regulation. There is one that we are using here in Europe. Sorry, it's called Eurocode. Eurocode is a standard to compute wind load over structure. So this is kind of a shared regulation among countries in Europe, and is dedicated for safety issue, not wind comfort. But still, it gives you some good number, I think. So there are basically two rules here to look at. If your topography effects increase wind speed by more than 5%, then you should take into account this orography. The other way to see the issue, if your slope is higher than 3 degrees, so that's about 5% slope, it will require to take into consideration orography. So remember, if you have slope more than 5% local slope, you need to take into account orography. Otherwise, you can deal as flat on your project. Another thing to see is how far I should take into consideration the orographic effect. Then here there is some kind of answer. If you have isolated orographic feature, such as a hill, so let's say this is about small hill for pedagogy. This is 10 meter high. You should take into consideration up to 10 times this height, so 100 meter around. It will affect the project. So remember these two numbers. 5% slope, you need to take into consideration orography, and 10 times the height of the obstacles. Okay, this was for orography. Now for land occupation or roughness, you have the roughness according to different land occupation. you have on the left part roughness of the city of 1 meter high, equivalent. This is building of 20 or 30 meter high. And on the opposite, on the blue line, you have the sea of, this is a roughness length about 1 millimeter. So there are two information here on the left panel. So you have the wind speed according to the height, and you will see that the wind speed increase with respect to the height above the ground. It will increase with some mathematical law. This is a kind of representation, and we will talk about that later. And the second information is that at 10 meter high, you will have 3 times more wind speed above the sea than above the city. So that makes a huge difference. On the right image, you have the wind speed, this time expressed in kilometer per hour. And well, same, you will see that the increase of wind speed is different for each land occupation with respect to the height. For example, the open country on the right will increase fastly than in downtown. Okay, so now let's introduce some shape or some law, mathematical law of wind speed. There are different formula to express the wind speed law. This is a log law here. This is one we are using in Europe. You can express with exponential. You can express with power law. At the end, this is very similar to each other. It depends on the coefficient behind. Here, the wind speed is expressed by coefficient. You have lambda, and this lambda depends of the roughness of your site, the Z0. And you see you have different class for grassland, open country, up to high density city. So the range, this is about 0.2, between 0.17 and 0.25, the lambda coefficient. It depends on the wind speed. URF, note that URF is defined at 10 meter high in open country. This is important to remember, in open country. And then you have the logarithm of Z. This is the height above the ground. And Z0 is the roughness length between centimeters to meters. So here, this law expresses the change of the mean speed from the reference wind speed at 10 meter high in open country to another land occupation at Z height with some gradients, vertical gradients. For example, from 10 meter to let's say 100 meter high. Okay, so we have seen some different classes. Now the reality is it's a bit more complex. If you have a look on your site, well, we saw very in the previous law we saw a transfer from open country to another one, and this is uniform. Here the reality is different, so you have more complexity. You have city, for example, you have a city on the right image, you have forest in the middle, and you want to transfer from the airport, which is at the corner left, to your house. There's a kind of a mixture of or a patchwork of roughness. So you will need first to know well, some kind of land occupation map. There one you can find is coming from ESA, CCI LC for land cover. There is 22 classes and only one for urban area. Spatial resolution is about 300 meters. You can find this map if you Google on Global Wind Atlas. You can display the roughness map all over the world. So it's quite nice. So you can have 300-meter resolution. Give you some idea. We have in Europe the chance to have more details with a program called Corinne Land Cover, with 4 classes for urban area, and resolution, well, 100 meters, but it can be up to 30 meters. So this is also open data. So you have your land occupation, okay. So now how can you mix roughness lens? Because it's not homogeneous. Well, there is some kind of answer coming from the safety vision from the Eurocode. They say that, for example, if you have a building of 30 meters high, you should look around a radius of roughness influence. And there is some kind of law. They say it's on the top right. They say it's 23 times the height of the building. So here 30 meters, power 1.2. Okay, so this makes about 1.3 kilometers. So you have to look around 1.3 kilometers. What is the roughness? They will look every 30 degrees, some kind of discretization, and look for the lowest roughness lens that represents more than 10% of the surface. So this is a safety vision. So it means that it will reinforce the real wind speed by taking the lowest roughness. The reality will be smaller. It's not exactly in the reality. It's not exactly like some kind of average of roughness. It's more tricky than that. Only other tools can estimate roughness. So here, for example, CFD tools. Here we have WT for that, or you can look for on wind tunnel. But at least it gives you some idea. Okay, so I would like to give you some help with what I call the first aid kits. Simple, but I think quite powerful. First thing is which station should I pick for my study? If you have choice, if you have multiple choice, you should always pick the weather data at the airports for 2 reasons. The quality, because for safety reasons, there is no alternative than excellent quality of wind data. They are recorded every 40 hours over the year with high frequency, so it's well set up. Second thing is it's located in open location, meaning that there is no disturbance around. It's mostly in open country, and there should be no obstacles nearby the mast data. And moreover, if your mast is located in downtown, you have buildings around the mast, and these built environments will evolve with respect to the time, with years, because of the urbanization. So wind data will be affected by change of buildings. That's why you should always pick a weather station at the airport if you have choice, of course. Then you should also check weather data quality. Okay, first thing is time step. If you get ultrasonic anemometer data, it can be smaller than 0.5 seconds. You have on the right part in the blue lines, you have this kind of record. So you see it's highly disturbed, lot of turbulence. It's not for a purpose. If you try to use what they call the 3 seconds moving average in the dark, this is still too much turbulence. What we need is the intermediate results. You have the dash green vertical horizontal line. This represents 10 minutes average, and this is the mostly used for wind comfort. Mostly used because I know for Netherlands, for example, they use 1 hour time average, but very depends of the country rules. The other thing is a time frequency. So there are quite a lot of frequency available. In the mostly wind engineering practice, we use hourly data that have been averaged over the last 10 minutes. You should check also the units. Make sure that it expressed in probably in meter per second. You also need to check the quality. Very simple. Try to check the mean and the max for you and the direction. If you have values such as 999 for a long period, that could be an error of sensor. So be careful of that. Another thing you should also check is what is the time of record. This should be the last, let's say, 10 years. I would recommend 5 years if you have no other choice, but 5 is the minimum, 10 is the recommend. And because you need to catch big events such as El Nino, La Nina. And you should also take the last 10 years. Last 10 years because also because of the urbanization. I have here capture on the right, bottom right image. You see the progression of urbanization from the 90s to 2011. You see how the urbanization will grow. So imagine that the roughness so it will difference and the wind speed will be affected. That's why you should take the last 10 years. Okay. Last thing is how to deal with obstacle nearby. That's why you be careful if you have obstacle nearby your mast. How to correct it. This is a tricky question. So that's why it's preferred to avoid that question. And another one is that when I transfer my data, we strongly advise you to transfer above your project, because for some reason we don't want a single building to affect the quality of the wind data. We prefer to deal with a statistical approach to correct using the log law with the correct final land occupation of the city. Otherwise, the data will be affected locally. Okay, let's move to some example. So we will compare the wind conform map using analytic law to a more complex approach using CFD with our in-house products. And let's see what will be the impact on wind comfort. I will go through 3 projects. Okay, and we will use log law formula. So from the airport at 10 meter high URF in open country to the site. So Marseille first, we transfer data from the airport to the city or dispersed house. So you have topography on the bottom, on the top left, sorry, and the bottom left, you are land occupation. And we transfer from the airport, you see the arrow pointing to the bottom right. So we transfer to dispersed housing, some neighboring. So if I come back to the table I showed you before, this is lambda equal to 0.21 and roughness Z0 equal to 0.25, okay? And I transfer from 10 meter to 100 meter. This gives me a ratio of 26, 1.26, so it means there will be 26% more wind speed at 100 meter high above the sea, above the city, than at 10 meter high above the airport. Okay. So I will compare the result from the log law to a more complex approach using CFD with our product called WT. So it gives me same results, about the same results. So 1.26 for the log law, and CFD give me 1.25. So almost the same numbers. And more interesting things, if you have a look on the windrows, if you compare, what give me the approach on the CFD is pretty much the same as what I got at the inputs. There is no deviation. So orographic effect was very light here in this case. So no need a complex approach here. That's a relief. Okay, let's move to another example. That was done in Paris. So this time I transfer from the airport to another suburban area. Coefficient is a little bit more higher. We are in Paris, 0.5 for the roughness lens. So it gives me a ratio of 1.24 with using our log law. And the CFD, well, CFD gives me something different, much higher. We have 45% more wind speed at 100 meter high than at the airport. And log law give me less wind speed. Well, this is because of our roughness simplification. We pretend that we arrive to an homogeneous roughness or land occupation, and it was not the case. If you look at here, the land occupation on the bottom image, you see you have a lot of different color, meaning you have different land occupation, contrary to Marseille. It was much homogeneous. Here it's a mixed. So first, the roughness stance was not simple at that, as not only the destination, it's more complex than that. And the second thing is the orography effect. You see on the top image, we starting from the quite high altitude to the city, to Paris. There is some more than 150 difference meters. So that's why that explains the difference between these two. So this gives me 20% error on my wind speed at 100 meter high. Okay, next question is it important? 27%, does it matter at the end on my wind comfort classes? Maybe this is not important. So let's have a look on my project. In Paris, I will use wind comfort criteria for France, 3.6 meters per second with 1 sigma of turbulence, comparing wind comfort using log load transfer and wind comfort using CFD using WT approach. And we have colors, classing comfortable activities. So purple is comfortable for any kind of activities. And on the opposite, red is not comfortable at all. So we see that because CFD have more wind speed, 27% more wind speed, we have more red. So this is actually crucial. You see that it affects our results. It's more uncomfortable, more for pedestrian activity in my situation compared to if I use simple log low. Here it makes sense to have relevant wind speed. Okay, let's move to the last example. So we transfer from our net mast. So this time it was not at the airport. It was in the city. So city to neighboring. So in this time, it was not possible to use directly the formula I explain you later because URF hypothesis was at the airport, and it's not the case here. We can actually derive URF, a new URF, by using this law and claiming that URF equal to UZ divided by the right-hand side. And we reintroduce the wind speed at the airport in U, and we derive URF. So get the new URF, and we re-inject these results to transfer at our project. So if we do that, even that, we have another issue, is that we have orographic effect very strong. This time it was not simply a hill like in Paris, but it's a mountain effect. So if we compare what we have at the airport, not the airport, sorry, it's a mistake. What we have at the master data, it was prevailing wind coming from the east. And now above my site, you see that direction, the prevailing direction has changed because of the mountain effect. And this is the drawback I want to show you if you use only mathematical rule to change mean speed, not taking into account the change of direction. So that's why you need a more advanced tool to correct that. I want to show you now some last question is, where can I collect data, weather data? There are several ways. First one is to ask to your national weather data provider. So we have here Météo France. In France, we have Met Office. There are many of them. There can be open data. There can be sales service, depending on the country. There is another one coming from NOAA. So far, they have an agreement between all the national providers to collect data and to store them in NOAA in US. So it's worldwide and available for free. You can find also EPW. EPW is a weather data that is, let's say, has been averaged over the 20 or 30 last year to get you a typical year This is available for wind speed, for solar, for temperature, for many parameters. So you can use this as an input. You can use also weather data. I know there is a meteo norm. So just be careful of meteo norm because whenever you have orography, it will interpolate between known station, but wind direction is not good. So be careful of the meteo norm software. You can use also what we call reanalysis of mesoscale data. So basically, it's a code that solves weather simulation, and you can find many services can do that. It's funny because today we're going to launch our new wind portal. So it's a good moment for you to look at that. So you can find in this portal of Meteodine wind around the world, and you can download time series over the last 10 years or for the future if you want to have a look on what will be in the 2050 or 2011. That's possible. Well, 2100, sorry. So in a long time. So you can find that on our new web portal, or you can, although you have other competitor doing that. And also another possibility is coming from Urbawin. We have done a lot of effort to integrate in Urbawin wind database for Europe, for North America, for Israel, for Oceania, for the main cities, and we correct using WT CLD products. So many ways to collect data. Okay, so I think I cover what I wanted to talk about today. And now it's time for you to ask us questions in the question panel. We have some time for that. Otherwise, you can send us email, of course.
Yeah, thank you, Guillaume. So yeah, as mentioned, Guillaume, you can have the chat panel at your disposal to ask your questions within the 5 or 10 minutes. And also you will have access to the replay of this webinar and all the Excel file summarizing the PDF file summarizing the answers from your questions. And I think we have a first question about how to calculate radius of roughness, as you mentioned earlier, Guillaume.
Yeah. Okay. So you will see more. It's easy when you get the PDF. It's 23 times the height multiplied by power 1.2. This is the radius of the roughness. Okay. How do you recommend to create land occupation map? Sorry. So I say Google Global Wind Atlas, and you will have land occupation over the world. It's called not land occupation, but roughness length. So you can have an idea every 300 meters. After, if you really want to get some more details, you need GIS software, just as QGIS Global Mapper, and download land occupation map. But it's a skill, or it's a job, I would say. Okay, another question. What is the difference in accuracy between numerical estimation and real data? So I said this, it's about 5% difference for our tool. we compare to wind tunnel. And we compare also from a case in Japan called Niigata. It's available on our website. Another question for you, yeah, for the portal.
Yeah, one question is regarding the portal. So the wind data portal will be available through a website by the end of today. And this is a link you will have access through our website, so metadyne.com. And also you will have access directly if you ask us directly by email. We will be happy to send you the direct link to connect to the platform.
Another question is about so some local methodology recommend to take altitude or height at 100 meter or 150 meters, sorry, above the ground. So if with our product Urban, you define what is called href at 150 meter, and you integrate weather data at this reference surface. Okay. Another question regarding influence of a building. So if you have a building of 100 meter high, so this affect the wind up to, so it depends between 1.4 or 1.6 times the height of the buildings. So if your reference wind speed is at 150 meters, this is the limit, I would say. Otherwise, you need to use log low of this 150 meter height to get a little bit higher. Otherwise, it's potentially affected. Okay, another question. A lot of questions today. This is good. Very happy. Question about, this is a general question. How is CFD is working to compute over a whole domain? Okay, this is a different product called WT. You will compute over a large domain, let's say 10, 20 kilometer radius. You take into consideration much larger orography and land occupation every 30 meters. And you compute the wind over this large area. So the wind will be deviated and will be affected by the land occupation. We have more details about the other project if you are interested. Okay. There is a question about LiDAR. So in Urban, there is no LiDAR correction so far. There is not this kind of product. So I suppose this is more for wind energy purpose. Unfortunately, we don't have this kind of, usually this type of technology.
Technically, in urban planning project, we don't use the correction. We don't correlate the wind data, LiDAR data, but we usually do it when we have a wind energy project. Okay, next question is regarding the data
from a built-in area. I said this is tricky because if you have obstacles nearby, your wind data will be affected. So it means you need to correct, to remove this influence, and it's not easy. That's why I prefer to recommend to use non-disturb situation at the airports. And also for other reasons that the urbanization will evolve with age. So you have an obstacles nearby today, maybe tomorrow the obstacle will be different. So it will affect differently your wind data. It's very tricky question tricky situation to use station in the built-in area.
And I think maybe the last question for today, and of course all the other questions we didn't have the time to answer yet. You will have an answer by words with the replay of this webinar.
I think we cover all the question.
Maybe the last one. Okay, so I think we are good now.
Yeah.
So thank you all for your participation. And of course, feel free to join us by email or to contact us for a project or for advice or training session. And we will be happy to answer you. And of course, stay tuned to our next evolutions.
Thanks, Ivan. It was the last webinar of the year. So very happy for this year. And we propose you a new webinar, new subject next year. So let's say the Guillaume is tuned about that. So have a good day, everyone, and see you next time.
Thank you all.
Bye.
Bye.